about optimize your code, an introduction to profiling for HPC and AI applications. Three speakers today. The first one is me, the other one is George, and Spiros at the back. Just a few introductory before we start. So yeah, my name is Christodoulos Stylianou. I'm a research engineer at Castor C here, and the person responsible for the trainings and skills development for the EuroCC2 project. My area of expertise is in high performance computing. And currently I'm working on the intersection of HPC and AI. Okay. So today this training is funded by the EuroCC2 project. The EuroCC2 project effectively is a part of a pan-European project under the Euro-HPC joint undertaking, and it involves more than 30 countries. And its aims is effectively to identify and address the skill gaps, both of the European ecosystem, but also the local ecosystem of each country, so that it sort of bridges the gap between the HPC, AI, and high-performance data analytics, both in the academia, in the industry, but also in the public organizations and so on. And its goal is also to coordinate cooperation across Europe, so that it ensures that every country has the same skill set available. And Castor C here is a National Competence Center, or NCC, in high performance computing. This is since 2020, and now it's in the second, third year phase, hence EuroCC2. What we do in the EuroCC2 project is effectively we liaise with the local computational communities. We sort of identify our main computational needs and provide tailored services. For example, we provide consultation, so this can be 1 or 2 months of a short-term collaboration. We can look at the code, we can sort of advise you on the next steps you can take, and so on. And we also assist with resource provision. So this means if you want to access, for example, our HPC facility like a Cyclone, feel free to let us know, and we can give you guidance on how to do that. Also, if you want to have, let's say, access to European HPC, to the Euro HPC ecosystem, we can also facilitate that, and we can assist you with the process. And finally, the last service we provide is trainings, such as this one today. We aim for monthly events, both to public, academia, and industry, but also to custom events as well, depending on the needs. So, last slide before we dive in. Today, we have the first 3 presentations will be sort of to prepare you for the hands-on session that comes after the break. First, I will be talking about the profiling basics. I will try and help you understand some metrics and some tools that are available for high-performance computing. Then George is going to be talking about profiling, how to profile AI applications. And Spiros will give you an overview on how to scale up your application from 1 GPU, let's say, to multiple GPUs and so on. And finally, after that, there's going to be a 30 minutes break. And after that, there will be a 2-hour hands-on session, mostly on profiling AI applications. So depending on what you want to do, you can feel free and jump back in or stay for the remaining of the training event as you see fit. Okay, now are we good online? Great. Okay, now let's start. So the first part is about profiling basics, how to understand metrics and tools for HPC. And the goal of this presentation is sort of to give you an introduction to key metrics, explain what is profiling and the basics of profiling, and give you some idea on the tools that you can have access to for analyzing your high-performance applications. We already said that. No need to introduce myself again. So the objectives for today is threefold. Effectively, an introduction to profiling for HPC, then a discussion for metrics, and discussion of metrics for performance evaluation, and then sort of explore some workflows and some tools for performance optimization. So first of all, what is profiling really? So this is a process of analyzing an application, looking at its performance, and then identify the bottlenecks. So why my application is slow, for example, or in which parts of the code I see the most bottlenecks that sort of hinder the performance. And it's quite important to know these things because you need to optimize your computational workloads accordingly and depending on the bottlenecks that you have. And if you do that, you can enhance the scalability and efficiency of the whole application. And at the end of the day, reduce the time to solution that is interesting to you. There are different types of profiling. We can have performance profiling, where we're interested in looking at the computation and the communication performance. There is also memory profiling, where we sort of monitor the memory usage of the application and memory leaks. These are very nasty, by the way. If you have a memory leak and you don't know about that, your application might work perfectly. Well, if you do that on, I don't know, a few gigabytes of RAM, but as you keep iterating, at some point your application might fail and you might not know why, right? And you can spot that using tools for memory leaks. And then the other one is I/O profiling, effectively measuring the efficiency of your input-output operations, like such as reading or writing data to the disk. This is also very important these days. Has anyone heard about the 80-20 rule by any chance? Not in this context necessarily, but in general. So the 80-20% rule says that effectively, in terms of profiling, it says that programs typically spend 80% of their runtime in 20% of the code. So if you wrote 100 lines, you're only interested about the 20, right? And at the same time, it says that the programmers typically spend 20% of their effort to get 80% of the total speedups, right? So once you do that, the remaining 80% of your work will be to try to reach to 100% of speedups. So stop. Don't do that. You should stop before you over-optimize, or at least have a plan on how to do that. And the idea is when you do profiling and optimization, you don't want to optimize the parts of your code that do not really matter, and start optimizing after you really understand the performance bottlenecks. So you need to know your application before you start optimizing it. And there are, let's say in this example, for example, just to give you an idea on what I mean by that is, let's say you have two independent parts. You have A and B. You cannot see. Oh, perfect. Okay, so let's say you have A and B here. You have two independent parts. The original process, it takes this amount of time for A and this amount of time for B, right? And one is executed after the other. If you make B 5 times faster, then you sort of reducing this blue figure here. So you make it like, as you can see here. But if you make A 2 times faster, you sort of reduce your computation time by much more compared to devoting all that time to make B 5 times faster. Okay, so you can only do that after you analyze your application, after you profile your application effectively, right? So there are different tools and metrics for profiling serial code, and by that we mean code that usually runs on one CPU core. We care about execution time. Effectively, we measure how much time each function took to run. We care about instructions per cycle. Effectively, this indicates the efficiency of the CPU usage, how well we utilize the CPU. We also care about cache hit and miss ratios. So if you're aware that modern processors, they have in between, so you have the processor and you have the main memory, and in between you have some sort of fast memory. It's called cache, and the idea is you use that as an optimization layer to accelerate the memory transfers effectively. And if you have a lot of misses, effectively you're talking about an application that effectively is heavy on the memory, and that's the main limitation of the application as well. And you can figure it out by looking at this metric. Then you also have the branch prediction accuracy. So effectively, if you have an if statement, for example, how much time, and you want to predict the compiler sort of, or the runtime predicts um, which branch of the if statement is going to be taken with time. So if you get that right, a lot of times you can accelerate stuff because you know which instructions to execute before even you have decided in which part of the branch to branch in. And the branch prediction accuracy effectively shows you an indication about how accurate you're doing that. And this is useful for conditional heavy code. If you have a code that is full of if statements, for example, if you have a high prediction accuracy on the branch prediction, then this is a good indication that you have some sort of structure in your application. And then I/O wait time effectively measures the inefficiency in disk operations. So effectively, you measure how much time it takes to write and read an application, write from the storage. And different tools you can use. I think I've ordered them in the order of complexity to use them, but they're not really complex tools to use. So gprof is effectively an open source profiler by GNU. Effectively, it just shows you different parts of the program that take most of the execution time. This is good for C, C++, and Fortran applications usually. And it just imagine that once you run it, you'll get a report about how many times each application was executed. It took that much time and so on. Perf is, again, a Linux profiling application with performance counters, and can also add some instrumentation on your CPU, performance counters, trace points, and dynamic tracing. So this is much more complete profiler compared to gprof. And then you have Intel vTune. So this is an x86 profiler by Intel. It has a nice GUI that you can use, and it's good to play around with. And it can also provide you with uh, various reports and schema and figures and so on that will help you understand the performance of your application. Now, we've talked about serial performance, but we also care about, these days we care about parallel performance in a way. And the reason this is happening is because the free lunch is over. Effectively, over the years, even until 2000s, early 2000s, the way we used to get increase in the performance application was effectively by switching to the processor, by switching our processor to a processor that has a faster clock, right? But early 2000s, since early 2000s, the clock rates are no longer increasing. So I think this is around this plot here. So if you see the plot, we care about the green one, and you see that the frequency of the processors has sort of reached a plateau. So we don't really make processors faster anymore, right? What we do instead is we exploit performance through parallelism mainly. So now we're in the multi-core era. So we make our CPUs to have more than one core, and we exploit these performance gains through parallelism. And now it's up to the programmer to sort of extract this performance. There's no free lunch anymore. And the optimization of the application as a consequence becomes quite challenging. So effectively, you have increasing application complexity. You might have applications that have multi-physics or multi-scale and so on. You have increasing machine complexity. So now we have very big machines. We have hierarchical networks. We have hierarchical memories. I've talked about caches before, for example. And we also have more than one type of CPUs. We have the traditional CPUs. We have multi-core CPUs with many cores and so on. And we have accelerators as well. So understanding the application performance and also optimize for that it has become quite challenging, right? And the parallelization is often limited by various overheads. There is no one overhead that you care about. So you might have non-parallelized regions. For example, you might have code that is still serial, that still runs on one core. You might have I/O operations. You might have communication, and other dependencies, and so on. And the theoretical speed up, so how much you can accelerate your code, is often limited by the serial part of the application, and this is the Amdahl's law. So, for example, if you have, let's say, an application that is running for 10 seconds, right, and you optimize only a bit of that application, maybe a function, right, and that corresponds to 5% of the code, the remaining 95% is still serial, right? So you can accelerate only 95%. You can accelerate only that 5% of your application as you increase the number of parallels that you have, right? So the idea is that you are always limited by how much serial code you have and so on. Now, we also care about sort of different stuffs when we're talking about sequential or serial performance factor or parallel performance factors. For example, for the sequential or the serial case, when we talk about computation, when we want to accelerate computation, often what we do is we want to choose the right algorithm, a better algorithm that is sort of faster in the way that in the complexity in the sense. So if you have an algorithm that takes n squared steps to complete, you might want to change to an algorithm that takes n steps to complete if that's possible, right? That's what you care about. Or you can take advantage of the compiler and use the optimizations that has, in order to optimize the software for you before you even run it. Also, you care about caches and memory in a way that is effectively, there's not many things you can do here, and you sort of rely on the compiler, but still, that's another thing that you care about. And then you also care about input and output. So these are the sequential factors, performance factors that you care about. In parallel, you care about other things as well. So you can think of the sequential performance factors that are still relevant, but you also care about partitioning and decomposition, how you split your application domain effectively so that each parallel component takes a piece of that. So how you do that, for example. You care about communication, how the different parts of your application communicate together so that they reach to a common solution and so on. You care about multi-threading performance, how well you're utilizing all the computational resources and synchronization and so on. And you'll see some good examples in later talks as well that show you an effect of, when you're waiting for things to synchronize, how this can affect your computation. And a traditional profiling workflow, okay, it looks better there. It's sort of an iterative process. It's not happening once, right? So there are roughly 4 steps that you follow. And the first one is, to prepare your application. You need to identify performance goals and configure your tools. So by looking at your application, what do you want to achieve effectively, right? And then once you know what you want to achieve, you should know what tools are at your disposal and what each tool will be used for. And then you have also measurement. You need to collect data with those profiling tools. And then you need to analyze those results and figure out the bottlenecks using some particular matrix and so on. And once you do that, the 4th step is the optimization, doing refactoring of your code or improving the performance and so on, right? And then you go back again and see, do I have now different goals? Do I need to adapt again? And then you repeat this process over and over again until you reach out to a good point of your application that you're happy with. And we have different key metrics for identifying the HPC performance. We have the global efficiency. This effectively measures the overall performance of your application. This breaks down into parallel efficiency and computation efficiency. Each one gives you a different metric for each, a different overview for each. So you have parallel efficiency also breaks down more to load balance efficiency, how you distribute the work across processes, and communication efficiency, which is effectively how much time you're losing in communication and so on. So now we're gonna go through each one. The first one is global efficiency. So this is a measure of how well your program performs as a whole, right, after you parallelized it. So it combines effectively how efficiently your program uses parallel processing and computational resources. And why this matters, effectively, it sort of tells you the overall health of your application's performance, right? If you have low global efficiency, then it means that you need to change something, either how you parallelize stuff or how you process stuff, right? And if you have high global efficiency, that means that your program is running efficiently both in parallelism and computation, okay? And you can measure it by multiplying the performance efficiency, the parallel efficiency with times the computation efficiency that we'll see in a bit where they come from. Now, the first part of global efficiency is parallel efficiency. And this sort of describes how well the execution of your code is working in parallel, right? So this means how efficiently your program uses the available processors or the available threads and so on. And this matters because the parallel efficiency can show you bottlenecks related to imbalances or excessive communication in parallel execution. So for example, if you are doing a lot of communication between the different processes that they're using, then it might be a good idea to, after you know that, it might be a good idea to optimize for communication. So maybe you want to switch to some communication avoiding algorithm, right? That effectively does less communication, but the result is the same. And parallel efficiency also breaks down into load balance efficiency and communication efficiency, okay? And load balance effectively reflects how well the distribution of the work that you have to different processes of threads is done. Effectively, it just measures how equally the work is shared among the available processing units, right? So, for example, if you have let's say 3 processes that we see here, right? So on the bottom figure on the left, we see an example of good balance. So you have the computation, or the processes do the same computation, or the processes do the same amount of communication, and so on and so on. So this is an example of good load balance. An example of bad load balance is what we see on the right, where we see, for example, process 2 in the first computation phase takes roughly the average of P0 and P1. So by the time that now P1 finishes computation, you see that it has to wait for longer communication. It has to perform longer communication before it proceeds to computation and so on. So if all processes finish their tasks at the same time, then load balance is high. So it means we distribute the work quite equally across all the processes. If one finishes much later than the others, the load balance efficiency is quite low. And this effectively, if you have uneven workloads, makes some processes wait for others to finish, wasting resources and time. And effectively, the takeaway message here is that effectively, once you do that, once all processes wait for others to finish, then you always have to wait for the slowest process to finish before you move on to the next piece of the computation. Now, communication efficiency, it's a measure of time lost due to processes waiting for data or communicating with each other. And communication overhead can effectively slow you down, especially if you have large parallel systems. So if you scale out to systems like Lumi, for example, which are very big systems, how you communicate across processes plays a major role in your application. And you can break that down into serialization efficiency and transfer efficiency, but I think we're going to skip this now. But the idea is, let's say you have 3 processes. The first one does this computation and then has to wait for that much communication before it proceeds further on. So the compute time here is, let's say, 1 second, and the communication is 5 seconds. And the efficiency for that is 1/6. The P1 takes, let's say, 4 seconds for computation and 2 seconds for efficiency. And the third and the third process here, it takes 5 seconds and 1 second for communication. The efficiency is 5/6. And to compute the communication efficiency, what you need to do is take the maximum of the computation time over the total time across all processes. And in this case, it's 5/6, which is 83%, and so on. Okay, I'll skip this. And now computation efficiency effectively is it measures how efficiently your program performs calculations. So we've moved ahead from the parallel stuff, communication, and so on, and we now care about how fast we can compute stuff. And it shows effectively how well the computational workload scales as you add more processes. So let's say you increase your resources. After you do that, how much better was your performance, let's say, in terms of runtime. And the computation efficiency is computed by comparing the total time spent in computation for different number of processes or threads. So you take multiple multiple numbers for that, depending on how you increase your resources. And high computational efficiency means that your program scales well, so you avoid extra overheads or unnecessary computations, right? And you can have low computational efficiency for two reasons. You might have more processes. As more processes execute, you might execute more instructions as well. For example, you might do some extra computation in order to decide how you break down your domain across the parallel components. Or you might have the same number of instructions computed, but they actually take much more time in parallel. Right, and this might happen because you're using shared resources across all the processes, for example, like memory channels and so on. And the first metric to identify that is instruction scaling, and measures effectively how the number of instructions executed changes as the program scales. And ideally, the number of instructions should stay constant, irrespectively of the number of processes you're using, or ideally grow or even grow minimally as you add more processes and so on. And the instructions per cycle effectively measures how many instructions your CPU executes per clock cycle. And high HPC means that the CPU is effectively used. So you really want to extract all the available performance out of the CPU. Okay. Now, okay. So this is a recipe of the steps that you could follow, for example, to start from an application that you've never profiled to an application that you know what's going on under the hood, for example. And the first step is background. Look at the background, effectively document your application about how to reproduce the simulations and so on, how you can reproduce the data that you generate and so on. And this will be important for comparison later on, because let's say the last thing you want to do if you optimize an application is to get the wrong results, right? So you need to have a baseline in place where you can compare the optimized results, for example, with the results that you have in the first place. So if these are different, then you need to understand why they are different. Are they supposed to be different or not? And they don't really have too much on the bit level every time, right? But you need to be aware of what's going on there. And then you need to figure out the application structure. So give an overview of the application structure itself. And this is, you don't really input that into somewhere. It's just for you to be able to keep track of what's happening. And then once you understand the application structure, you can identify the regions of interest. So these are effectively regions with heavy workload or high I/O communication or memory communication and so on. And then once you do that, you can start do the first profiling runs to understand the scalability, for example. So this is the first way to understand how your application execution runtime effectively increases or changes as you add more resources and so on. And then you start breaking it down. You start looking into more specific things like application efficiency, effectively how much time is spent for essential communication and computation. You might check typical issues like communication overheads or imbalances, and you start looking at these metrics that we've described earlier on. Then you investigate how the work is distributed among workers, and then you look at the serial performance. So you actually look at the computation in regions without communication and so on. And finally, well, after you've done all this, you can also play around with communication. Look at how all the available computational units communicate together and so on. So just to give you an idea of what you need to understand before you even run the application and so on, let's say we have this WRF application, right? And this is like the weather research and forecast model. It's available online there. So if you want to write down something before you start even do profiling, then an example will be WRF 4.0. So you also provide the version of the application you're using. It's parallelized using domain decomposition techniques. So you keep track of how you parallelize stuff. And then where communication between domains are done via MPI, and each domain can be parallelized using OpenMP. Don't worry if you don't know what MPI is or OpenMP is, but this is just the programming models that they have used to sort of parallelize stuff, right? And this is important for someone that is going to process the application to know what's going on in the application. Then you start giving some information about the data. You're using grid sizes, which include volumes from different ranges, and they have output files from 300 megabytes to 2.2 gigabytes. And this is again important because if you are going to profile on a high performance computing system, you need to know how much storage you're using, so that if you're using something in the terms of terabytes, you need to ask for the people to give you access to that amount of storage. And then you narrow it down to a specific test case. For example, I want to do weather forecasting, right? And I'm using this Morrison double moment scheme with some transfer model for long and short wave radiation and so on. And then you do time integration with Runge-Kutta, third order, and so on and so on. So you need to be aware of what's happening in the application before you even start profiling. And once you do that, you can identify some regions of interest. You can do preliminary profiling and understand where the challenges are. For example, it might be some computational kernels. It might be due to the domain decomposition, or the computational load per domain has become too small and so on, or too large and vice versa. Or it might be some IO kernel. So for example, after each hour, you need to write back to the disk, and you need to write, I don't know, 2.2 gigabytes of data or 2.2 terabytes of data. So this might be a hot area that you might want to explore when you do profiling and so on, right? And okay, so based on that, we did the background, we did the application structure, we identified the region of interest, and now we can start with the scalability analysis, for example. So after you identify all the regions of interest, you can investigate the overall scalability of the whole application, and you can see how the runtime changes as the number of cores is changing and so on, as you add more resources and so on. And you can run with different number of processes, and you'll get the first hint on parallel overhead and so on. It's important to keep notes of how many resources you're using, because if you want to repeat the scalability analysis again, it's important to repeat on the same resources, because if in the first time you were using, let's say, 4 CPUs to run, and now you've went through the whole process and you start again, and you compare the result with 8 processes, it might not make much sense to do that, right? So, and this is, for example, what we might expect at the end of the first scalability analysis. So you have some strong scaling of the computational kernel, and by strong scaling we mean we keep the problem size the same and we increase the resources as we go on. And you see that we have at the bottom, we're increasing the number of processes, and at the y-axis we see the time per integration step, and we're looking at various test cases, right? And you see that, for example, in the largest test cases here, we see that our runtime effectively reduces, and it reduces in sort of a linear way, which is good. And we see at the small case, at some point later on, it just resets at the end as we add more processes and so on. So this is a good point to start looking into why this is happening, for example. And if you look at the second region of interest, which is about the input-output, again, for various test cases, now we look at the time per write in seconds, and we increase the number of processes. So we see that, well, it doesn't make a lot of difference, right? It's pretty much constant every time, apart from these cases here, which I don't know, something went wrong. For example, here it might be the case that you have a lot of overheads from the many people using the system and do a lot of heavy I/O operations, and this is a shared resource. And at the time you were running that, you had this spike and so on. But this is sort of an indication that, for example, your I/O is serial, right? You keep adding more resources, you have the same time for one write. And then you can look at the performance gain through parallelization using speedup plots. So here we're looking at run times. You can sort of have a reference time, well, the serial time, and you can divide that with the actual time at every step of the process you're using. You can get speed up. This is very easy to look at the scaling behavior on how this sort of scales as you increase the resources, and keep a note of the reference times because it might get lost. It gets lost in the speed up plot, so you need to have it later on. And this is the idea. And at the end of the day, you can identify limiting factors as well using these plots. For example, for a specific case, you see that you look at the execution time of various. This is using a profiler now, using a different function specific to the application. As you do that, for example, you can see that for different functions, you see different scaling behavior. And even as you add more processors, you have the opposite effect. So your runtime now actually increases instead of decreasing, and so on. And that sort of shows that effectively your domains have become quite small. And finally, some profiling tools. Most of them are from BSC, Barcelona Supercomputing Center, and Jülich Supercomputing Center in Germany. These are tools that they have been implemented for a lot of years now. These are some good tools. Some of them we have here installed on Cyclone as well. Some others we can install if you want. And the very good thing with that is if you are interested in these sort of applications, there are a lot of tutorials and videos available and material from the POP COE. So this is a center of excellence, again, within the HPC JU ecosystem. And it's actually specializes on performance optimization and productivity. So this might be a good way to start. So just to sum up, even before you start optimizing, you need to identify your major computational kernels, understand the scalability and bottlenecks, and different bottlenecks might need different solutions and so on. And in order to get a better overview beyond scaling and timers, you can use profilers so you can analyze individual parts of the code. And again, what are your performance bottlenecks? Is it parallelization? Is it scalability? Is it I/O? Is it memory? Is it and so on? And then after you have identified that, do you have plans for optimization? Do you optimize parallelization? Do you optimize computational kernels? Do you switch your code to using libraries, for example? Or do you port them to GPUs and so on? So that was all from me today. Thank you for your attention. I think I ran a bit over time. Yeah. Do we have any questions? Okay, thank you. Online, do we have anything online? Any question online? Okay. Thank you for listening, and I'll now pass on to George. He'll be delivering a very interesting presentation. Now, I think it's the interesting stuff in how to optimize AI. Yes, but now you'll have hands-on as well on that. So I think it's this one. Is it this one? Okay, great. Let me set it up. Okay. All right.
Well, good morning, everyone. As Chris said, I'm gonna talk a bit about today about profiling, specifically AI applications, and we're gonna delve a bit deep on some techniques, some best practices, and some key metrics. First of all, a bit about myself. I'm Yorgos. You can call me George. I'm a research engineer here at the Cyprus Institute in Castor C. I mostly work on data science and machine learning projects. And I'm also the awareness and communications task leader for EuroCC. Uh, so the goal by the end of this session is to equip yourself with some basic skills on profiling. First, we will explore the metrics that matter when you're profiling those applications. And we're not just going to be looking at CPU usage and time. I'll be covering some more specialized metrics that are crucial for understanding your application's performance. Next, we'll get some hands-on with PyTorch profiling tools. And when PyTorch generates the traces and the profiles, we're gonna see how to actually visualize them and how to interpret them. Since collecting data is only half of the battle, you need to actually understand what it's saying. And by visualizing them, we'll be able to see some patterns more easily. And yeah. And then we'll put all this knowledge to practice, which is the most important one, and actually modify our code to speed up our training or our inference performance. So let's talk a bit about why profiling these AI applications is particularly crucial. And it's important when using shared resources or paid resources. So when you're using an HPC system, for example, you want to identify the resources that you're going to need. So you're not taking, for example, 3 nodes when your application is only running on 1, because another person might need to run on them. Or if you're running on the cloud, for example, and you're training a model, well, if you're paying for 4 GPUs and you're only using 1, you're going to regret it when the bill comes. Yeah. These tools can also help us identify some bottlenecks. So again, when you have a lot of GPUs and only one is being used, and you see your CPU usage, for example, at 100%, then something is going wrong, and your data loaders, for example, aren't being fast enough in giving your GPUs data. And it's important because as you scale up your application, some trivial steps might not scale up correctly. And profiling is a way to find those problems out. And in my opinion, it's also a really great debugging tool because you can see your stack traces of what function is calling what function, and which function takes most of the time. And it can really help you when you are debugging your model architecture, for example, when you see some layers having gigabytes of worth of layers when it doesn't make sense to have those big layers there. Now let's focus on some of the metrics. And one of the most important ones is the GPU utilization, which, yeah, important. And here we have 2 different runs that this is from TensorFlow. We're going to see it later on. And on one example, you can see on the left, this GPU utilization is at 58%, whereas on the right side we have 90%. And we aim to be over 80, so we are, at least efficient. And these are running the same job. It's training an efficient net model. And when you see something like that, it's again, it might be something with your data loader, for example, that's taking too much time to send data to the GPU, or it might mean that your batch size is not good enough, and your GPU doesn't have enough data to actually utilize all of its streaming multiprocessor units. That's what SM means. And then the next important GPU metric is the memory utilization. I'm sure many of you, while training, you reach the out of memory error. That's the most common one. And that's why we actually want to see the usage and see some spikes. And that's why we aim to not fill up the whole VRAM completely up, so we can leave some room for some spikes. And we aimed for 80 to 90%. And in these two examples, it's the same ones as I showed before, the same runs. And on the right side is the low GPU utilization, and the peak memory usage in this example is 8 gigabytes, and that's running on the V100s, which has 32, I think. So anyways, over 30. But on the left side, we have 28 gigabytes. So we are utilizing around 80% of our memory. And it's important to actually use those two metrics along each other, because they can show us they can show us a complete story of what's going on. Yeah, for example, we might change. Yeah. So here we can see clearly the bottleneck according to the memory utilization and the memory utilization and the GPU utilization. And yeah, as an example, I can give to why this is happening. You can imagine the GPU being a factory worker, and they are actually standing there waiting for raw materials to build the actual stuff. So yeah, that's what is happening right here. And some CPU metrics, CPUs are important. They are mostly used for data loading, preprocessing, augmentation, and stuff like that. And what we measure in those cases is mostly the time per batch retrieval. So the time it takes for the VRAM to be filled up with the data in order for the model to start computing on it. And that's important because GPUs work best when their memory is full, so they have enough data to work on, so they can actually utilize the whole processing unit, the SM cores. And an example we're going to see later on for the data transformation course I have here is the tokenization time. And this is especially important when you're working with NLP tasks, for example, and when you are initially loading text and you are tokenizing it on retrieval, you're gonna tokenize the same thing over and over again for each epoch. So it doesn't make sense to do that. You should actually pre-compute the tokens and then start using them. So we're gonna start looking at some tools. This is the most basic one. I believe most of you should have used it by now. It's the NVIDIA SMI. When you type that on a server or on a computer with a GPU, it's gonna give you gonna print this, and it gives you important information like other than the temperature and the power usage, which if it's your own system, you should think about. If it's system that's hosted by someone else, you shouldn't be worried about that. And you can actually see the memory usage of each GPU and the utilization of the SM cores. And along with that, you can use it for some debugging. For example, you can have a process that froze up and you can't stop it. It will give you the process ID at the bottom with the process name and how much memory is used by each process and on what GPU it's running. But since whenever you type NVIDIA SMI in Presenter, it's just going to print it one time. It's not going to update itself. So I usually do watch every 2 seconds, and it updates the NVIDIA SMI every 2 seconds. And now we can see some actual PyTorch code. This is going to be in the examples later on. And yeah, so here we just use the torch profiler to profile. We have schedules, and this is important because when you don't actually schedule your profiler, it's going to produce massive trace files when you're running especially long training jobs. So in this example, this loop after the ASP_prof, it's basically a step, sorry. And for each step, we have, in this example, we are waiting for the first one and we're not profiling at all. Then we are warming up for one step, which basically gonna take out all of the initializing time, which you don't need to take into account when you are profiling. That doesn't affect your code because when you're actually running inference, you're not gonna be worried about that. Then we're gonna be actively recording for the next 3 steps. And we're gonna repeat the cycle only once. So by the end of this training loop, we're only gonna see 3 steps in our trace, which is enough. And yeah, when you're seeing the memory utilization and stuff like that, if you put the with stack equals true, it's actually gonna record which function called which, and that's gonna give you a much more complete view of what's going on in your program. And once that's done, and you actually print the profile that has been created for you, you will see something like this. And on the left, it's the names of the functions that were called. So if we see in this example, we put a record function with the name, so we can easily identify it in stack traces or on this profile. And here we're just copying some data under the batch processing, and then as an example, we're just looking for the model computation. And as you can see, here is a nice example of what a good training loop should look like, where the model computation takes most of the time, above 90%, and the rest is just very low. On the other hand, you can see this example, where the data loader takes 85% of the total time, and the model computation only takes 13%, which if you are training a model and 80% of your time is actually copying memory from disk to GPU, then you're wasting a lot of resources. And I forgot to tell you about the self CPU and the CPU total. And that really means the CPU total is the total time for example, the batch processing took, and the self CPU time is not taking into account any child processes that were launched from within that scope in this example. So yeah, we go back here. We are basically defining scopes, and we are profiling those scopes specifically with a custom name. And then all of this is just a simple way to view your profile in the terminal, but you can actually import all of these logs and profile and traces into TensorBoard. It was actually developed for TensorFlow, but they have plugins and PyTorch natively supports logging into it. Some of you may have used it mainly for logging your loss or your accuracy and stuff like that, but it actually has a lot more functionality in it. It has built in the Chrome tracer, which we're gonna see later. You can have some nice overviews of what's going on. So for example, the GPU summary I showed before is just from here. You can see the execution time in a pie chart, which is more easily digestible instead of the terminal print. And you can actually choose between the workers you have. Spirit is going to show you a bit about that later. I'm only running examples on one GPU for this session. And the views there, you have a lot of options. A really nice one is the module view, which is specifically for profiling your model. So for these examples, we just extended the EfficientNet model. And as you can see, the first sequential part of it and the total time it took to compute the 3 steps. And this is a stack trace of the model only. So you can see what each layer, how much time is each layer is taking in I don't know what this type of graph is called. It's really common when you are profiling. I think Chris showed something similar before, but it was only with 4 cores and 4 steps. Then the actual GPU memory utilization, where you can identify spikes. You can see how much time it takes for the GPU memory to get filled up. So since we're only running a couple of steps, we don't see a plateau over the top, but you'll actually, when you're running on large batch sizes or large data sets, let's say, or large models which take more computation, the time that the memory is allocated at peak, it's gonna be longer. And here it's a really nice trace view of what's going on, and it's an important. It's why we actually create our custom scopes with custom names, because when you first see this thing, it's it's a mess. You see a lot of functions that you don't know what they're doing. You didn't actually call them. So we actually, yeah, that's why we put those those record functions we showed here. Batch processing. And this is an example of the data loader I showed you before, of the example I talked about before. As you can see, for each next data, which is the iterator of your data loader, takes 60 milliseconds. Whereas when we pre-compute the tokens, and each next iterator only takes 150 microseconds. So that's 600%, no, 600 times faster. I'm not wrong. Yeah. And we cannot talk about GPU profiling without mentioning Insight. We're not gonna really use this because you either need to install the UI locally or set it up with the X server on SSH tunnel, which we're gonna set it up for today. And you basically run your application with with Insight. So in the terminal, you're gonna type nsys and then some flags if you want, some custom flags, and then python.train.py, let's say, and it's gonna record even NVLink bandwidth or PCI bandwidth, which is really important when you are really fine-tuning your communications and your transfer speeds. Yeah, are we back on time? Perfect. Well, do any of you have any questions?
So my question is, how easy it is to do profiling on PyTorch? Like, let's say I have a model already. I wrote the code, and I want to start profiling it. Do I need to do a lot of modifications? I'm pretty sure you're gonna show that in the tutorial later on, but do you have to do a lot of modifications to start working on that, or is it just what you showed here?
It's just this. I mean, if you import a module and then you execute your training steps and everything else inside the scope we defined, the profiler scope, and it's gonna record it. You just need to, put in a directory. I mean, the examples on PyTorch site is like 10, 15 lines long, and it's that easy.
So you can do a basic example using this.
Yeah, for sure.
Okay, cheers.
But I believe it's really important to, when you're profiling specific parts of your code, to actually use the record function, because you're gonna be looking at the trace for 30 minutes just to find where your function is. So that's really important and a good practice.
There's another online question.
Yeah, sure.
Sergio's asking if the Torch profiler is specific to Python code only.
Torch profiler. Can you write Torch in, what other languages can you write Torch with?
I think you can write in C++. I think it should be available there, but I don't think it's gonna be that easy to use.
Yeah, I'm not sure on how to answer that. I never written Torch in C++. I can look it up, but yeah.
Oh, I think what you're looking there though, it's C++. Like these function names are C++ names. So I think it should work, yeah, in any case. But how you do that is a different story.
Yeah, I don't know how you're gonna launch TensorBoard using C++. I think you're gonna have to use Python for that. So
it depends on the output, right? It depends what
the TensorBoard UI.
Yes.
It's actually running a server.
Yes, you can launch that, but you can load a trace that it's from C++ code, for example.
Yeah. You can even load these traces. This one in particular, where is it? Yeah. This one is just the Chrome tracer. If you have a Chrome browser and you do Chrome semicolon dash dash trace or tracing or tracer, I'm not sure, you can just import the JSON file. That's your trace, and it's gonna give you exactly this thing.
Okay. So, any other questions, guys?
There's a question. Yeah. Thanks for the nice presentation. And my question is about comparison between TensorFlow and PyTorch. So, as far as profiling concerned, which platform has good tools for the profiling in specific and in overall in general?
You said TensorFlow has good.
I mean, which one has the good tools, the TensorFlow or PyTorch?
Well, I haven't profiled TensorFlow code. TensorBoard is their application, so I'm sure they have. No, they actually have. I'm sure they have some profiler built in, because let me put this back up again. Not this one. This one. This one. So at the top here, when you see inactive, it's actually specific TensorBoard plugins. And I remember seeing something about, I remember seeing a profiler there, which is not the one we're using. We're using the Torch profiler, can be seen here. Let's see if I can zoom in. So here, yeah, we're using the PyTorch profiler, whereas if we go here and press this, you're gonna see the profiler, which I believe is TensorFlows.
Is there any comparison? Like which one is?
I haven't used it, so I'm not gonna make you.
Thank you.
I'm not gonna answer. But I'm sure it's more than fine.
Yeah, of course. Thank you.
Thank you.
And now we move on with Spiro's presentation on how to scale your AI code on multiple GPUs.
Okay. So hello from me as well. I'm Spiros. I'm a research engineer at Castor C, working for the EuroCC2 project. My work mainly focuses on computer vision and time series analysis and anomaly detection for meteorological data. And today I will be talking about scaling your applications to utilize multiple GPUs to train your AI models. So why should we train on multiple GPUs? So let's consider that over the last decade, CPU performance hasn't scaled dramatically. But in contrast, GPU performance has grown at a much faster rate. The exponential growth in GPU power means that we can have larger gains in training speed and be able to handle much larger models using GPUs rather than CPUs. Also, a lot of state-of-the-art models, like some large llama models or maybe some very deep YOLO models, are massive in terms of parameters and very computationally intensive when training them or running inference. So training these complex and deep models on just one GPU can either be very, very slow or actually just not feasible due to memory constraints. So by spreading the work across multiple GPUs, we can handle more complex architectures in a practical amount of time. So the next question is when should we utilize multiple GPUs? So the answer is quite simple. Either your model is too large or too complex to fit on one GPU or run in a reasonable amount of time on one GPU, or your data set is too large to be handled by a single piece of hardware. As we can see here from this, it's not very visible, but you can take my word for it. Modern training for the large language models requires an exponentially large amount of data to get a not so great return in accuracy. So as the amount of data increases, the amount of devices they use to train these models also increases, and the ways they choose to parallelize their models also become more and more complex. So there's two main types of parallelism. There's data parallelism and model parallelism. So data parallelism is the simplest and most commonly used approach for parallelizing your applications. The benefit is that it's very easy to implement, as we will see down the line. And it scales well with more data. But it has some drawbacks, as in the model has to be loaded on each device, and the data is split amongst those devices. We will talk more about that later. We also have model parallelism, which you can split it down into two subsets, which is pipeline parallelism or tensor parallelism. In pipeline parallelism, the model is split across different GPUs layer-wise. So one GPU will essentially run the first subset of your model. Some other device will have a different subset of the model loaded onto it. And parallelizing is done via communicating from the different devices so that they transfer the data effectively through them. So the model is essentially split vertically by layer. For tensor parallelism, on the other hand, the model is split horizontally, which lets us handle bigger layers without running out of memory on a single GPU. So one big benefit of this approach is improved memory efficiency for very large models. But Vangeli? Absolutely, yes. Yes. For example, something like ChatGPT, like the new GPT models, they are so large, they probably use all three of these methods at the same time. And the complexity of training these models becomes, there's a lot of overhead when, yeah, like communication-wise, you can imagine like having to communicate in a fast way through different GPUs, like for example, using InfiniBand or NVLink or PCIs. You will need some specialized communication hardware for this. So yeah, all of these methods can be used to parallelize your applications. Each of them come with their benefits and their drawbacks. So for the purposes of our hands-on sessions, we will be implementing data parallelism. So let's begin with a simple forward pass. So in a forward pass, we first read the data from some source, transport the data onto our devices, pre-process them, split them into batches and so on. And then we transport our data to the model. So when it's in the model, the data propagates forward. At each layer, we calculate the activations, and eventually reaching the last node, the output node, where we calculate the output, the loss, the gradient, and then we back propagate through all the layers to perform our optimization step so that we train our model. When we are training in parallel, when we are implementing data parallelism, let's start with a simple scenario where we have multiple workers. Each worker can be a single GPU or a separate machine with one or more GPUs. And instead of having a GPU store a different part of the model, we keep a full copy of the model on each GPU, which means worker 1 has the entire model, worker 2 will also have the entire model, and so on. So the difference here is that we divide our training data amongst all our workers. So worker 1 might get the first chunk of the data set, worker 2 will get the second chunk, et cetera, et cetera. And each worker will run a forward pass and the backward pass on each subset of the data and compute the gradients locally. This means that each GPU will independently calculate the weight updates needed for the parameters, but based only on the portion of the data that it sees. So as a result, the training steps can run in parallel, significantly speeding up the process of training large applications, because you can process multiple batches simultaneously. But the problem is that because gradients are calculated locally, you must have some way to communicate within your GPUs. And we must also ensure that everything is synchronized so that suppose, for example, each GPU will reach the output stage at the same time so that they can communicate the gradients with each other and calculate some kind of, and accumulate these gradients so that they can backward propagate them to update their parameters. Yeah. Exactly. So think of it like this: you have your database here, split it amongst like 2 GPUs. Okay, each GPU will process half of the data in batches. Okay, and at the end, you will calculate some kind of gradient on both of the GPUs. Okay, at the same time, of course, synchronized. This gradient will be accumulated in some way, either by averaging or some other maybe more intelligent way of aggregating this gradient, and you will backward propagate the same gradient through the network because you want the model parameters to actually update in the same way. You cannot have a different model parameter here than there, or else training. Yeah, they average the gradient, the accumulated gradient between all of the workers. It is. Yes, both of the GPUs, both of the models loaded on each GPU will backpropagate at the same time, the same gradient. Everything must be synchronized, or else you will have, at some point, you will have some communication error. We'll see some of this in code so that you will understand. So the main advantage here is it's very scalable. As you increase the number of workers, you can train on much larger data sets and achieve results faster. But the challenge is dealing with the overhead of communication. Exchanging gradients between the workers, it can become a bottleneck as the number of GPU grows. But for let's say a medium-sized application which has a lot of data, suppose you want to train a YOLO model on a big data set, data parallelism is a great way to increase your throughput. So I guess in short, data parallelism in short, you load the same model on all GPUs. Each GPU processes part of the data, and then the gradients are synchronized and backpropagate. So there are many ways to implement data parallelism, but the one we will be focusing on today is using PyTorch's data distributed parallel, which is a streamlined and efficient way to implement data parallelism at the module level in PyTorch. So unlike general data parallelism, DDP is integrated, integrates PyTorch's models and communication libraries, which is making it well suited for easily scaling up your applications on multiple GPUs with not much effort. A good standout feature of this library is the ability to automate synchronization and gradient averaging in a seamless way during the training loop. The communication is done using backend infrastructures like Nickel and CCL libraries or GPUs, or Glue for CPUs, which these backends essentially serve the purpose of ensuring the communication overhead is minimized, even as you increase your devices. Yeah, I won't talk more about this. Go too deep into DDP. So let's. So this is an overview of like a typical cluster architecture. You have multiple nodes. Here we have 2 nodes, host 1 and host 2. Each node has 2 GPUs. Each GPU is associated with a global rank. So the global rank is a unique identifier for each process across the entire cluster. So if you have 2 GPUs, if you have 2 nodes with 2 GPUs, you have a total of 4 processes, which will be assigned, let's say, global ranks 0 to 3. global rank essentially tells each process exactly where it stands in the entire distributed setup. And out of all the GPUs involved, which GPU it is. Okay, so global ranks are used when communicating between nodes. And yeah, that's their main purpose. Or suppose you want to perform some operation only once, like print your training results. If you were to print your training results each epoch on all GPUs, will have X amount of training results printed. But if you print only on, let's say, global 0, you will have a more neat application and a better way to visualize your training results. So next is the Next is the local rank. So the local rank is the identifier of a process within a single node. So there's each node runs multiple processes, one for each GPU, and the local rank tells the process which GPU it's pinned to on that node. So if you're on host 0, local rank 0, you might correspond to GPU 0. And on host 1, local rank 0 is again will be GPU 0 of that node. So suppose how these local ranks are used in data parallelism. For example, you might not want to download the entire dataset on each of your devices. You might want to download the dataset on, let's say, rank 0 of node 0, and just communicate the data between the devices in that way. And you do the same for both of the local ranks on each node. So here you can see it better. So this is a simple script that outlines how the code looks when you use data distributed parallel. So first you will define a main function, which will start when you run your script. So the main function will be something like multiprocessing.spawn, which spawns a number of subprocesses to execute a function, which in this case is the worker function. Okay. In this main function, we essentially tell our script to launch as many workers as we have GPUs available. So next we move on to the function that the worker function, which will contain like variable declarations and the training loop. So first we define our global ranks and initialize the process group and specify the world size and the local ranks along with the backend that we will use for the communication across multiple GPUs. So next we download the data as in the way I said before. We choose to download only on rank 0, and we will then share with the rest of the GPUs on that node. A very important command when working with data parallel is this dot barrier command that you see under the cursor. Control is there. You can also be here. You can find out here. Thank you. Thanks. So then this dot barrier command is very important, as essentially this command tells the workers to stall and wait until every single GPU comes to the same point in the code. This is how synchronization is maintained throughout the script. Because suppose when you will want all of the GPUs to have downloaded both rank 0 GPUs to have downloaded the dataset, and then you move on to the next step, or else you will have a synchronization error somewhere down the line. Suppose you reach the end of your training loop, okay, and you calculate the output, you will put the barrier there. Yeah, so that everything waits, everything reaches the end of their training. Yes, yes. Every time you put this, you will add more synchronization time, but it's a necessary evil because you need everything to be synchronized.
Can I add something here? I mean, what we see here is if local rank is 0, then you want the rank 0 to download the data, but you want the rest of the process to copy the data from where they were downloaded in rank 0, for example. So you need to add this barrier in the middle so that you ensure that rank 0 downloaded the data, and then the others can go and get it. If you don't add that there is a chance that, if you are not local rank 0, you might try to get some data that they don't even exist there yet. That's the idea of the barrier.
You can do this on every process. Training, where you're validating.
No. Only in the main important parts of your training loop. Everywhere where you will want things to be synchronized. Suppose, like I said before, the example that I said before is suppose here, okay, you will want to put a disk barrier here because you want at every point every GPU to reach the same point before you backpropagate, and then essentially you will add these barriers whenever you will get errors in synchronization. If you don't add them, you will get errors.
Actually, if you add more than what you need, then what will end up happening is that at every step you're gonna take, you have to wait for all the processes to come and do the same thing. Exactly.
Yeah.
So it's like an art, and you want to use it only when it does affect your result, your correctness effectively.
Exactly. So why is profiling multi-GPU applications important? So firstly, of course, it's you optimize your performance. When you're running tasks across multiple GPUs, you want to ensure that each GPU is actively doing useful work. Profiling helps you see if your GPUs are being fully utilized or if some are sitting idle while others are overloaded. And by analyzing these metrics, you can tune your parameters like batch size or use different data loading strategies to get the most out of your hardware. So the second and very important part is bottleneck identification. So multi-GPU environments often suffer from communication overhead that we mentioned before, especially with data parallel. And profiling and pinpoints where and when these slowdowns can occur. It could be during the gradient reduction across the nodes, or maybe your memory on one GPU is insufficient. And you can address these issues. You can spot them and address them. You can spot them and address them in ways such as like I guess utilizing maybe smaller batch sizes or enabling mixed precision training to improve your communication patterns. And finally, there's resource management, which profiling will help you distribute your workload more evenly across your GPUs, so you don't have a straggler slowing down the entire training job because they were overloaded in some way. Or you can reduce idle time by looking at how your clusters are working in sync. So some of the key metrics for multi-GPU profiling is, of course, GPU utilization. You want each GPU to be consistently busy. So if one GPU's memory is overloaded, you risk an out-of-memory error or slowing everything down. If something is underused, then you're leaving performance, well, essentially performance that you are paying for. And ideally, your utilization should be balanced so that each GPU is pulling its weight. So next is communication and synchronization. So when training in parallel, GPUs will need to exchange gradients and parameters. So the communication will introduce overhead, and the more GPUs you have, the more overhead you will have. So a high communication overhead will mean less time spent on actual computation, and you can reduce these, reducing these synchronization points and using more efficient collective communication operations will help speed things up. And lastly, load imbalances. I mentioned the side effects before. Essentially, load imbalances is you strain your GPUs with more data, some GPUs with more data than others, creating the issues we mentioned before. So this is what a typical computation and communication graph looks like when using a PyTorch profiler on multi-GPUs. You will see something like you will see a histogram essentially with as many bars as you have GPUs. And each of these bars represent how much time your GPU spends doing a certain activity. For example, computation in blue, overlap and communication is red and yellow respectively, and other processes that also slow down your training. So ideally, you will want your overlap and your communication to be identical, meaning that all communication is overlapping with computation, which means you are being as efficient as you can with managing communication and computation at the same time. This example here shows something known as a straggler. As you see, every GPU is spending a lot less time on computation than this specific one here, the second one from the right, which you can see it clearly. I mean, the computation time is much larger, and this causes another issue where, because this computation time is so much larger, everything else, the communication time for all other GPUs also becomes much larger, because they essentially have to wait for the straggler to finish its operations, then they can communicate. This is also seen on this graph here. This is the synchronization and communication. Okay, we see this GPU here is spending a lot less time on synchronization, but that's because it's performing its computation much slower, and all the other GPUs they must wait for it before they can continue also their processes, their main processes, like actually communicating the results between each other and so on, and furthering the training. So this code snippet here is something you will see in the practical session later. So this is a function that sets up the distributed learning on Slurm. Each GPU needs its own process. The function relies on the Slurm environment variables such as like the local ID for the local ranks, the process ID for the global, and the world size, which indicates how many GPUs you have available. And these variables help PyTorch's init function to synchronize all the processes and enable this efficient communication between them using our backend, which is Nickel, because we're using GPUs. Additionally, torch.CUDA set device assigns the appropriate GPU to each process in the right format that it requires. Because, for example, here you will require something like a CUDA semicolon 0, CUDA semicolon 1, 2, 3, 4, and so on, to appropriately set your device. Here's how I do it. So next, this is going to be the actual model we will be training. We will be using to visualize our profiling. So we define our model, and afterwards we wrap it in this torch.nn distributed NDP, which ensures the gradient synchronization across all the GPUs during training. which enables the efficient way of scaling your multi-GPU operations. And lastly, we have we also have the function to set up our data, where we handle the dataset partitioning using PyTorch's distributed sampler, which ensures that each process only works on its unique portion of the data. And combined with the data loader, this setup will balance workload across GPU and minimize transfer delays. Let's stop. Yes. No, there's no issue. There's no issue. So lastly, I won't repeat, because this is essentially the same line of code that George explained before. And I guess that's all from me. Any questions? George, any from online?
One good thing with the distributed training is that if you have, on Cyclone, we have V100s that they have RAM of 32 gigabytes. And if you want to train on much more larger data, let's say, then you can use this and expand the available memory that you have. So if you place 4 together, it's like you have a GPU with 120 gigabytes of RAM, for example. So depending on your needs, you can also do that.
It's a great way to essentially boost your batch size without explicitly boosting your batch size code-wise. Because suppose you're training one GPU on a batch of 64, you can train, and that's the maximum you can utilize on one GPU, or else you will run out of memory. If you were to use this on 2 GPUs, you can scale it to 128, because essentially you have 2 batch sizes of 64, just distributed across multiple devices. Speeds up your training without affecting your accuracy later on.
But lots of but doesn't mean better performance, right?
Normally, if you use a larger batch size to actually make your performance a little worse, if you use a much larger batch size. But with distributed training, it does not affect you in this way, because you're just doubling the batch size. You're not explicitly increasing the amount of the data your model sees each step. You're just distributing that data across the GPUs.
So,
Yes, there's no question.
another question from that.
So that concludes the first section of this training event. We now have 30 minutes break for the in-person participants. There are refreshments outside, so indulge yourselves. For the online participants, we'll be back in 10 past 12. So 30 minutes from now. We'll proceed with the hands-on. The session will not be recorded, but will be online on Zoom. So please feel free to have a go yourselves, and you can ask us questions there if you're struggling. For now, enjoy the break.